I'm Graham Mueller. I did the simulations.
I'm Chris Parker. I designed the enclosure and soldered and programmed the visualizer.
I'm Bailey Sauter. I designed and built the amplifier and made the amplifier schematic.
I'm Thomas. I did the block diagrams, interface definition, and MATLAB script.
The goal of the project was to program a microcontroller to perform FFTs on data pulled from a microphone samples and display the result on an LED bar.
The design process began with the generic block diagram shown to get an idea of what we'd be working with. Then the interfaces were defined. In this detailed view, we can see that the mic took the signal from the outside environment and passed it to the amplifier. The amplifier, in turn, amplified the signal and also gave a 2.5 volt DC bias so that the Arduino could sample it. The Arduino sampled the wave and passed those raw samples through the serial port on a computer before calculating the Fourier transform and sending the appropriate data to the LED. The data passed through the serial port is read by a MATLAB script, which runs its own Fourier transform that outputs to a figure. The computer powers the Arduino, and the Arduino provides enough power to drive the whole spectrum analyzer.
The amplifier's purpose is to amplify the signal so that it is large enough to be read by the Arduino. This is an inverting amplifier circuit because the signal goes into the negative terminal of the op-amp. This circuit uses the LMC6032 op-amp and electret microphone, which were included in our lab kits. The resistors, capacitors, protoboard, and solder used to build the amplifier were sourced from existing personal supplies. As recommended by the datasheet, we used a 2.2 kilo ohm resistor between power and the mic to power the mic, and 1 microfarad of capacitance to get rid of the DC bias coming from the power source. The circuit uses a fixed gain of R2 over R1, which for our resistor values is 1000. This may seem like a high gain considering that the microphone supposedly outputs a signal with an amplitude of 50 millivolts. However, the signal was not this strong enough. The increased gain generated a more sensitive and precise signal at the cost of some clipping at very high volumes, because the amplifier output is powered with Arduino 5-volt pin. The voltage divider on the left provides a 2.5 volt input to the positive terminal of the op-amp, which biases the output signal by 2.5 volts, meaning that the output voltage will range from 0 to 5 volts rather than negative 2.5 to 2.5 because negative voltages are unreadable by the Arduino.
The circuit was simulated using LT Spice with a focus simulation placed on the frequency handling and gain characteristics of the amplifier. Shown here is the simulated microphone input, ranging from negative 50 millivolts to 50 millivolts. After amplification, the signal is not only significantly stronger, it is now biased to 2.5 volts. The Arduino's ADC is capable of sampling this amplified signal at any point. The amplified signal can be examined in the frequency domain, granting a view into the frequency handling characteristics of the amplifier.
For this project, we used 4 of these 1x2 beams with WS128B LED strips attached to them. I designed these enclosures for either end. This one's purely to hold the beams together. This one holds all the electronics. As you can see, the Arduino's in here. And the enclosure has holes for a power supply, programming the Arduino, a microphone, a power switch, and a button to change the modes in a future update. The code for this project was very straightforward and can be broken into 5 sections. First, there's a loop to take 32 samples from our microphone and add them to an array. A second array is filled with zeros. This allows the Fourier transform function to provide data on the real and imaginary axis. Next, the Fourier transform is computed. These 3 functions scale the sample data, then compute the FFT, then convert the imaginary numbers to their real magnitudes. Then, we use the constrain and map functions to scale the FFT values in the real array. This converts all the data to a relative number between 0 and the height of our display. These numbers are carried over to a separate array of intensities if the value at that frequency is increased. Otherwise, the intensity value at that frequency is reduced by 1. Finally, each row of the display is updated using the array of intensities, and a show command updates the display to show the new values. Each row contains code that either tells the LED in that column to light up in the column's color or display black depending on the intensity value at that column.
The MATLAB script runs in a finite state machine, or FSM, with two states, sampling and computing. In the sampling state, the script reads an arbitrary number of samples from the serial ports and stores them in an array. Once the proper number of samples has been reached, the current state switches to the computing state. In the computing state, the mean of the signal is subtracted, meaning the DC offset is taken out of the signal. Next, the Fourier transform is computed. This gives us complex numbers so that we can take the magnitude of the signal and then take the positive frequencies only, because the Fourier transform provides positive and negative frequencies. This is then graphed on a bar graph.
There are several next steps we could take with this project. We could use a language other than MATLAB for a faster FFT. We could use a faster microprocessor to reach Nyquist sampling frequency. We could use a better, more sensitive microphone than the one included in our lab kit. We could compare the simulation to real-world data, or we could add an auxiliary input rather than the microphone.